SVIT welcomes you all to the first guest lecture of our 2-month-long RASVERSE event. And what a better way to start than none other Mr. Saurav Karmakar taking a session on flexible robotics and its application in aerospace and medicine industries. Mr. Saurav Karmakar, as he describes himself as a roboticist, a term generally referring to a person who is involved in the designing, programming, developing, and testing of robots. All in all, he's a robotic enthusiast. He's the founder and CEO of Infinios Tech, a company that is into making eco-friendly and clean tech robotic application-based products. He is also the Indian chapter chair of Space Renaissance International and has mentored NASA Space App Challenges in Italy. We are very honored to have you with us, sir. Sir, over to you, sir. Thank you, sir.
Thank you. Thank you everyone for joining and thanks for the introduction. So this session will be like more interactive. I'll be very happy to take questions. I think and the topic that I'll be discussing, it's like a kind of from basics, little bit about the soft robotics, flexible robotics, and the components, the primary things that we use there, and also little bit of applications. It could be from little bit of basics to little bit of advanced, and what I am doing presently, and the things that I've already done. So there might be more pictures than write-up. So if you have any questions, either you can stop me in between, or you can also ask me at the end of the session. Anything is okay for me. And apart from that, there might be different other things. If you think that I can also help you guys in something, just let me know. So I'll just share the screen and we'll start. Hope my screen is visible to everyone.
Yes, sir. Loading.
Is it okay? Once it is visible, just let me know.
Yes, sir. Now it's visible.
Thank you. So yeah, so this is like the overall theme. Then I'll be like talking, going towards the and by the way, in between, if there is any, if you can't see screen and all, please stop me because I'm not sure looking at the Discord and all. So just let me know if it is not visible, or you can pause me. So I'll be talking about what is assistive robot. Initially started because initially the robotics is very important for the different kind of activities related to human civilizations. Not only that, when passive or actively, that means like it could be from the social point of view, from a different kind of medical industry, education, like the basic fundamental stuffs where you can see robots. Apart from that, also we can see a lot of industrial robots and all. So that's the kind of definition. Obviously, the definition is like changing according to the time. So I just leave it to that. But when I'm talking about flexible robotics and all, it has certain things which is coming the area basically. One of the areas actually when you talk about the medical industry, it's called human robot collaboration, or maybe sometimes it's called human robot interaction. So if you see the image, you can see a manipulator, and there might be some task supposed to be done by the robotic manipulator, that means arm, and the end effector, that is the gripper, and the human is also there. Now it could be any sort of task that can be performed by a robot, but why we need human robot collaboration? So in the era of industry 4.0, or maybe I can say that it is coming or upcoming or it's already there. So the thing is like we know the industry 1, 2, 3, and like 4.0. So basically, till now we have seen the robots which are working on the different kind of industries and all. If you see the car manufacturing and such, it's huge manipulators which is like building the cars very soon. But now the thing is like it's very important that we need intelligent robot and also decision making. But we already know that if we think about the intelligent robot, we are also a lot of scientists are working on AI, ML to make the robot intelligent, or maybe a little bit of CV, all this all sort of combinations and all. So we see that the robot is also becoming kind of intelligence, but sometimes it's very important. Like human is like human brain or all these cognitive things that you see. It's not like a simple thing. It's like very complex stuff, and a robot to reach that level, it needs like huge data. And I mean, in the point I'm trying to say, like the mechanisms and the way, the formula, all these things, like each and every from the basic level, it's very important. So we need, especially for when it comes to the healthcare, surgeries, assistive robotics, we need decision making quality, which is at the moment presently we can't see in the robot in the decision making. Not like I'm talking about the serious cases. Maybe in the small application you might see that, but in the serious sectors and all, we can't see always that robots making certain taking some decision when there is a risk factor or there is a possibility of damage. That's the reason we need human to take the decision, and robot is for the precision. That's a very important term for both of us. So if you can see that, what is the potentials? Like as I mentioned, that precision, flexibility. It's not the flexibility that I'm talking about the structure, but flexibility means here we're talking about like the way the things can be uh, programmed and the coexistence of robot and human. If you remember the robots, like a lot of failures of the robots, if you see different tests, like maybe lakhs or millions. You can see a lot of robots, even like when it's testing, like maybe there is a possibility harming the human body nearby or something like that. So we need a flexibility that it can actually work together without damaging each other. Obviously, human will not damage the robot, but obviously it's other way. The thing is like also like for example, it's very important. We're talking about Industry 4.0, and we need some standard robots or robotic arm manipulator or standard robotic system, which is basically available globally, and then different kind of performance we can do. That means like different means in the sense like the standard should be the same, but different places, different customized situations and all, we can actually do that thing. And the last thing is like the high customize. If you remember the previous generation robots, it's not that much like in terms of that the variable perspective if you see, or the way that can be developed or it can be emerged, if I use that word. It's not like that. So basically, you need robots which can also like adapt certain things. Obviously, robot can adapt like that, but we have to make it like customized. Actually, we can actually let's say the universal gripper or end effector, which can be associated with many different kind of robotic arm. So that's a universal gripper. Okay, for example, I'm just taking one example. Or maybe two-arm gripper, which is like you can add to that robot with any robot, which we need like with a two-arm, we can actually manage. So it's a kind of the way that it can be customized or it can be associated with different kind of robots. What are the limitations? Like if you see the whole body control, certain cases it's still a problem, not possible always because. And when I'm talking about the robotic manipulator and gripper, initially it's obviously the rigid body robots. That means it can be with 3D printed or it can be with metallic body or hybrid or something like that. Mostly rigid. Very less you can see that rigid body with certain flexible structure or component structure actually. Next is like you can see that interfaces are also very important because you are talking about like human robot existence actually. And then it's very important that the safety, as I mentioned, that certain cases there is possibility that a robot is like there might be some sort of error or some sort of limitations that can actually stop working for the coexisting model. So those kind of stuffs are there. This redesign and other points are almost like the similar. So I'll be going a little bit from the rigid body robots, then I'll go to the flexible robotics. So very simple. If you see the from the left to right, it's like one of the famous robots, or the Vinci robot, which is mostly used for medical assistive or medical surgical kind of stuff. Industrial robot that you can see actually the manipulator. Educational also we can see a lot of humanoid robots. Wearables very important thing, and social robots. So mostly medical wearables are the most important at the moment or maybe at the segment. So the reason I'm giving example about rigid body robots also, sometimes we see the Da Vinci robot Da Vinci robot, maybe the gripper. Let's say there are a lot of researchers who are trying that we have a standard manipulator or standard robotic system, which is Da Vinci robot. Can we associate like soft gripper, which is made of soft material? Can we associate like certain sensorized gripper? That means it has certain threefold layers where the flexible or stretchable electronics are there inside that are like sensors. It could be chemical or it could be some sort of paste, basically not composite. It's not the right word. So some sort of paste actually, which is like biomedical kind of sensors that can be planted in such a way, designed in a such a way that it can maybe measure the pressure or certain sensitivity or some sort of skin related stuff that can be actually covered with when it's grasping on that time. So imagine the level of the robotic applications. Endoscopy bots nowadays, this is one picture actually, but nowadays there are a lot of robots actually, like it can actually crawl. It's like mostly it can be controlled like magnetic fields and all. Certain papers that you can find on nature actually. But anyway, so this is one of the examples. The reason I'm showing this picture, like it's like so small actually, and it has an entire all the IC, everything is there. It can actually go inside and check things and then come out. Due to COVID, I've also seen a lot of rigid robots or maybe hybrid robots, mobile robots, which is helping human to maybe that COVID zones and all, right? The fourth one is very interesting for me, clinical training bots. This is very rare that you can find that the clinical training bots. Basically, it's like the artificial human body where it can actually perform. So, for example, you take a robot and test on the animal for before the actual going for the human testing, human surgery. You go for animal or sometimes the rats and all. Like it's a part of the procedure, right? In the medical or medicine industry. But here, this is like a artificial human body, which has like the kind of artificial body parts, exactly maybe with the stem cells, maybe with the most sensorized structures and all. So when the robot will go inside, or robot will perform certain tasks according to, as per this body or as per this particular surgical environment, then we can get what is the impact on that human body. At least near to that we can estimate. So that's a very important, interesting thing for me at least. Industrial robot, I think this is like maybe most of your part of your syllabus. I'm not talking too much about it, but I think these are the standard of different robotic manipulators that might be already knowing or you already seen this. Social robots, again, I'm not going too much in detail. So basically different kind of social robots, which is like helping human for loneliness, psychological point of view, and then you might be already knowing about the Sophia, the robotic citizen. This is very important section. So we have actually worked on artificial muscle, but I'll come later about that. So basically, these wearable robots, you can see different pictures. So in that wearable robots, actually, what I am actually personally at the moment I'm doing, I could not include here because I think we're still at a prototype stage. So I'm actually working on dual body exoskeleton, hybrid, that's the goal. But we'll see from starting from digit and then we'll slowly move from the hybrid. So maybe next year, if I am getting the opportunity to talk to you guys, then I can actually share that a lot of stuff. I have 3 more projects. I'm talking about it one by one. So this is very important because I think how you are actually controlled with the brain signals and all these things. Okay, and then there are a lot of very beautiful things like the lightweight and the payload capacity. The battery should be very less weight, and then you have the flexibility. That means you should not feel like irritated wearing this kind of stuff, and it should be kind of little bit of universal. The reason I'm using little bit because there are certain limitations of each and every wearable robot, right? So you can see the different pictures actually, and this is not only for that like maybe physically challenged person or something like that. It's also for industrial purpose as well. Like you can see a lot of cases where the first picture that I've shown, this one. So in the industrial cases also, even in army, this kind of wearable robots are very interesting because it helps a person or human to take much more payload, and the capacity and the it will increase, and obviously the performance will increase actually. Okay, and people who are maybe what not having arms and all, unfortunately, they are actually using the bionic arm. So there is a wearable exoskeleton, and then a body like the prosthetic arm, bionic arms. So the thing like that I'm interested actually, like we are trying to make a like kind of practical things. Like the moment I talk practical, it's mostly like structuring the hybrids of robots with a structure, human brain signal control kind of setup. Plus, the payload capacity should be good, and also that fingers and all, it should be soft and everything. So it should not be like very mechanical looks. It's more like more bionic looks actually. Not only like looks, going to be like the structure as well. Okay, so this is like again two examples that when you robonauts, I think already Indian, I think ISRO has also like ISRO has already started working on some female robot actually like humanoid actually to launch on for Gaganyaan if I'm not wrong. So this kind of stuffs are already happening. Autonomous car, I think you know that Elon Musk and many other people, Google car, a lot of stuffs are happening. Educational robots, maybe one of you might be actually can bring or can make. Anyway, so one of the reasons that I want to portray is basically flexible robotics for space application. So this is the first kind of such kind of like the setup. If you see the picture, so there's the concept called lightweight solar cell. So this is like I'm using as a prototype. So here I'm using aluminum foil, and these are like if you see the structure, if you remember there is like a hand fans. I don't know whoever like experienced this in childhood. It's I used to call it like a Japanese fan. Basically, it's like able to fold and open. So this kind of things, right? So it's basically that kind of mechanism we developed, and here we have not used a single motor or whatever the rigid body, actuation or any kind of motor for rotation, any kind of stuff that we can use it. I've not used. My whole principle is to use soft robotic actuation system. Soft robot is not only like maybe the actuation from the pneumatics or liquid or something. Soft robot actuation can also be depending on the compliant actuator, flexible actuators. So one of the actuators is very famous. It's called SMA, shape memory alloy, which is made of nickel titanium. It has different alloys. Obviously, the most famous one is like the nickel titanium alloy, which is called SMA shape memory alloy. So we have taken like around 1 mm dia based SMA wire, and then we created like the actuation here, basically like opening and closing mechanism, as well as like it can be launched from the satellite or maybe a kind of box. So that's the concept, and it will open basically. This is the mechanism. So this is the first mechanism, then it will open. Sorry, this is the first mechanism. Number one, number two is this will open like this. This will be like 360-degree completely, and then it will basically be like open. So the concept, the reason I'm using, there are like two concepts. One is like soft robotic actuation, this nickel titanium alloy based wire that is like as an actuator. And then also we are using like a origami robotics principle. So origami is a paper folding technique, and this kind of robotic system is basically used like to optimize the area or volume or some sort of mechanism. So imagine that when rocket or any space vehicle is going like from it's basically launched from the Earth actually. The space inside space means I'm talking about that particular volume of the space inside the rocket or space vehicle is very small, and imagine that how much cost includes like whenever something requires to be sent to the international space station or beyond or something like that. It's like billions. So we need to find the way where we can actually launch the first set of stuffs, like for example solar panel, or if we have also worked on like something called Mars energy and that later. So there we need some nuclear reactor, 3D printing, for example, for space. So there we need actually some new system where we can actually use this SMA ware or this kind of flexible robotic system where it can autonomously launch also, number one. Number two, like it is cost effective. It has like magnetic systems and all, so it doesn't have that much cost. And also it will be like easily controllable, like you won't need too much power actually. It draws, the SMA actually draws little current, like high current is important. So that's only the backlog, but I think, and sometimes like it's a thermoelectric property, it has thermoelectric property, so it has like little certain limitations. But I think for example, for my setup, it is like the advantage is like it has 4-way open and close mechanism. That means you don't have to, like it's not that in single module you open everything, or and then you can't switch it off or you can't turn it off, something like that. So it can be closed or open based on the required, because nowadays we know that there are a lot of space debris and all these places which can actually harm the solar cell. So we can actually save this from that kind of setup. So we have that particular function, and it already got published in AAST Springer journal. You can also check it out. Second thing is like bioinspired soft robot that I'm working. So this is one of the small prototypes, which is not the actual. So it's like a octapedal soft robot made of silicon, but basically like it is made for the space exploration. One of my models, which can actually walk on the different terrains, uneven terrains and all. And I have another model which I'm actually writing a paper on. So I think again, as I told, like a lot of things will come next year or maybe the second end of this year actually. So basically, we are able to make pneumatically actuated soft robots. It is one of that actually. So basically, it is able to move to and fro, and then let's say it has certain. It's a small prototype, but I'm telling you, like, you can actually put a lot of different stuffs here, like small sensors, small batteries. So it's like all the autonomous setup we can do, and then it can also walk basically in a certain direction. That's the advantage. And in software code, the best thing is like the compatibility. I mean, compatibility with the environment. Because if you think about the robot and all, if anything got damaged, then you can't repair. But the thing is, here is the advantage is like if the stones and all, by any chance, because space is unpredictable. Any space mission is always unpredictable, right? You don't know, like you do everything, but you don't know there is an X factor which can actually damage your mission completely. So you have to keep your space missions less cost. I mean, it should be like less costly, as well as the prototypes or the product and the mission, part of the missions, like whatever rovers and all you are launching, that should be smart enough. It should be cost effective as well as it should be productive. And how long we can, I mean, whatever the duration should sustain actually that much time. So sustainability factor is very important every time, whether it is Earth or we're talking about the space. This kind of robots are very interesting. This is sort of like the first medical, biomedical, you can say the soft gripper. This is actually all are available on YouTube also. My personal channel is just like only the demo. So basically, it's a complete pneumatic gripper. It's focused on the finger, and then we are actually like having the capacity to carry like at least like around 30 to 40% more payload than this. I'm talking like the minimum, but I think the maximum it can go beyond 50% extra payload actually. And you can see the bending now. That is like the first, my case, like the first model that I have done. And we have seen like it can actually like, encircle different kind of objects. And the best thing is like even the both surfaces are plane, it is able to grip even the plane surface and it's not sleep. It's not like the slippery kind of stuff actually, because silicon and this kind of stuff is having this kind of property it might have, and then the Hooke's law, if you see all these things, okay, elasticity issues and a lot of stuff's happening. So in that case, it's actually sustainable. It's very good. I also have one more, artificial fingers, three fingers kind of. I actually, it's like a biopsy of the bird's finger, you can say, or three fingers based on the human fingers module and all. That I have developed with the shape memory alloy. So that in place of in pneumatic actuator, we have proposed the shape memory alloy. And again, that capacity is huge. Actually, like I have seen that, like it can actually hold like 60-70% extra weightage actually of its own. Weight and on payloads. So it's a very good progress in that direction. But the only advantage for like SMA based solutions that it could be the actuator. The problem is like it thermoelectric and sometimes it might burn and all. You have to think about how you are taking care of the control, because once it's bent, there is a concept in SMA called one way and two way actually. So one way is like, let's say once you bend it, you once you are done with the shape memory alloy mechanism first, when you put the memory what kind of shape you are required and find the final shape, then you connect the wires on both sides, and then basically you start do the power supply, even the heat or with the hot water, warm water, and also like the fire, direct fire from gas lighter or maybe from candle, it can work, but it's not distributed equally basically. So you need to make the heat distribution equally, and then it can actually bend it. For example, if my desired shape is this in the SMA, then it can actually bend like that, and then it can carry whatever you want, but it will not open it up. So that's the final stage. But two-way cases, like once it's dissipate the heat, and actually it comes maybe from U shape to maybe again the I shape of the wire, if you can imagine that. So that can actually happen. But for pneumatically actuated grippers, the advantage is it's not the like the rigid body robotic grippers or end effector, which is like on means completely on and off means completely off, or like opening or closing of 90 degree or 100 whatever, 180 or whatever. Like it's not like that. So whatever your object, according to that size, it can actually insert it or something like that. Basically, it will basically cover it or grasp it like that. So that's a great thing. And this kind of soft robotic gripper is useful for the delicate items like egg, or maybe you imagine the pastries and all. You can actually do that. You imagine that you can't hold any pastry with the plastic or maybe 3D printed or maybe metallic grippers with certain angles, and it will damage in certain level. So that's a disadvantage. In this case, these are the very good examples actually. Next is this one. So I mentioned about the Bionic Arm. The first step that I have done for Bionic Arm or the exoskeleton for hybrid soft robotics exoskeleton muscle wear. So this is basically made of the same where we make like the screen. This is also available paper on ACM Digital Library. It's called AIN Advanced in Robotics. So it's available already. You can check it. So basically, this is like made of again the helical SMA spring, and then we have this is the upper arm. You can't see maybe due to the light. It's acrylic sheet, transparent acrylic sheet. This is like a hook where we attach that particular arm muscle. We are calling it like an arm muscle here because it's like the muscle kind of acting like a muscle, human arm muscle. And then this is the lower arm. This is very much similar. One of maybe you're using for different mobile robots or different kind of modular robots or line volume robots in that cases. So here we are using this 10K ohm potentiometers and all, and then different. And here we are actually adding the payload. Again, it's very small, and we're trying to understand that what kind of if we can reduce the error here. So it's basically the control paper, robotic control. If I'm not wrong, we have used the PID and all, and we even tried sliding mode controls and all. But anyway, that's a different angle of things. I'm just giving an example that how we can actually model flexible robotics to different kind of biomedical application. This is the 2-3 things that I've shown from the creature point of view, from the human assistive point of view, from the direct assistive perspective for human as a muscle wear. So this actually can also be a part of different exoskeleton modules, but to see that how it will be operated, because when you go for customization and things, there might be some limitations. Okay, then I will go for the direct flexible robotics. So this is till now we have talked about like yeah, we have talked like discuss about the different kind of biomedical applications, little bit about flexible and soft robots. So if you see, there are 3 things that I've already shown. This underwater, these are like obviously not by me. If I'm not wrong, like you're from Harvard and MIT. So you can see this is like the hybrid soft robot. So basically, it's made of 3D printed palm and the fingers are pneumatically actuated. And it's so looking so original actually. Like it actually works like somebody is actually holding pencil. This obviously you can see the sorry, not octopus, it's jellyfish module. And these are like I think pneumatically actuated kind of this tentacles, and it also like here they have that pneumatic chamber maybe, or maybe it's all isolated like the chamber, the power. This the you can see there is a transparent tube which can actually actuate, and actually it can actually, if you see the video, it can actually rotate or move like kind of circular module. It can actually have that kind of movement or actuation. This you can see, this is one of the the original one, which is like the white color and silicon and all. It is actually quite different, but basically it has a huge capacity of like explorer, like being a robotic explorer. It's again controlled with a pneumatic actuator. This is the control board is here. It can actually walk on different surfaces. So this is like just starting with the pictures. So here I'm just talking about the actuators. So I mentioned about this shape memory alloy soft actuators, and this like you can see, this is the way they make. Like we can actually, there is a robot, if I'm not wrong, by MIT. They made this kind of a net system with that robotic actuator, robotic muscle kind of stuff, and then they use the shape memory alloy. I think these are like 0.25 mm dia of this each and everywhere, and then they arrange in such a way it can actually give you the earthworm movement actually, and they use some fabrics and all. It's really beautiful. You can just check it. Like, and then there is like a lot of flexible robots. When you're talking about flexible robots, like which has the folding mechanisms, in MIT you can find CASL lab. They're actually working this kind of stuff, like foldable and small foldable robots, which is like having different kind of mechanisms to fold it, like it can actually move it, and also from the Europe, I just forgot that EFL, there is also one lab is there. The professor, she's doing wonderful job. She's actually making modular robots, basically like this kind of foldable robots. They're very small size, very tiny, and it can actually change the shape according to desired requirement, mostly magnetically controlled, or maybe you can find one more robot which is underwater. It can go and it has like the laser control. So there are different kind of chemically. You can see the chemically something induced, or maybe magnetic. That magnetic propulsion kind of stuff they're using. So those kind of different kind of things are there actually. This is one of my favorites actually. This is like very static things, but the mechanism itself is compliant. So you can see little bit this translucent part of this picture. Basically it actually like a kind of clip kind of things if you imagine. So basically it's like a gripper, or you can actually move it according to that. So we can actually use in different mechanisms. So this is the different sectors that I have told. So pneumatic gripper, this kind of stuff, as I already mentioned that. So we can get a lot of data from the pressure and all, and you can actually miniaturize it. And this kind of things can be used like in the nerve related surgery, and then it can actually help you to basically collect, pick and drop, basically for different kind of surgical equipments, because those are delicate items, so it's very important. And we can actually add different kind of sensors on the surface, and it is, as I mentioned, that is like numerically power. So you can see this kind of pressure sensors and all these things are there. Okay, so when you go for a little bit of analysis, I think if you're a mechanical engineer, you know that beam. There's a lot of high parallelistic beam theories. So you can actually consider that when you're going for this kind of calculations. So this is one of the examples, and we can actually get the curvature and all this kind of deformation from the answers and many other softwares actually. Okay, so this is one of the my favorite things, that basically what I have developed is exactly the similar that I have mentioned. This also I have developed, but this is basically like the single finger that I've shown you, and this is like the 3 fingers or 2 fingers, basically based on that multi-gripper. And you use the exact thing as a different kind of material, fingers or palms. Okay, so the example that I can show, I think it is one of the companies in USA, it's called Robotics. So they are actually using this kind of pneumatic gripper which can hold different kind of objects. So this is the example. SM actuator, I just wanted to show that there are little bit of shape memory effects and all, where it's having the cooling and the change of deformation and all based on this kind of property. There are the three heating, cooling, and deformation. So this is martensite, austenite. This kind of states are there based on the molecular level. It actually changes. That's the reason it's happened. It's basic fundamental for the shape memory effect. Okay. Next, I don't want to go too deeper. This is the exact model. I can say almost like the exact model what I have shown on the bio-inspired paper. And basically this one is exactly the kind of similar model, but we have used different kind of control system. But I just wanted to demonstrate that how it works basically. So it's like the pulley spring mechanism. Here actually you can change with the SMA and all, and you can actually get different kind of calculation of the SMA speed. Okay, so one of the application that we have done is like it's called like Earth One movement. So it is like the actual spring. This is basically able to move forward based on that, like open and close of this arm. Like it's like at the moment it's open state. It is made of different kind of mediums or silicone, something like that, any whatever as per your requirement and the size of issue you can use that. So it can jump or crawl and all this. These kind of things are actually very good for space applications as well as gripping. So grasping and crawl, everything it can be done with a single bond. So very innovative. Okay, little bit of creature point of view, we can go. So basically, if you see, it can be done with SMA, it can be done with pneumatical also. For example, MIT, they have a fish which is able to keep that movement, the tail movement, exactly like the original fish. So biomimicry, you can see that video on YouTube. So, but here they actually you can use it with the tendon, you can use it with the flexible SMA wire also actually. If you want, like based on that, you can play with the actuation. Continuing robotic arm, little bit of that because this is one of the examples where you can get infinity degree of freedom. You can say I don't call it like it has like more than the n or something. So basically, it is useful for any kind of underwater or maybe somewhere you need more degree of freedom actually. Okay. Then you can use this. It can be used with a wire or tendon driven system, and here you can actually use the soft robots. We have actually like this is one of the examples. Without this, you can't make any manipulator. So flexible continuum arm is very important in any case of manipulator. If you're going for flexible robotic arm, this is the example. I think this is from I've taken from the some company start with F. Actually, just forgot the name. Tele. So this is one of the octopus tentacles made of that SMA web. You can see it can actually move, and this is you can see made of the kind of beehive kind of model. You can see this like the structures honeycomb model and all actually, and it has the gripper as well as the folding mechanism. It is also looking little bit of diamond shape if you can see. So this is from Italian Institute of Technology, IIT Genova, basically. It's really wonderful. It's underwater. They have used actually. And this is like one of the module. It's like a flexible gripper and flexible arm. Just I'm giving example so you can look at it. This I already mentioned. These are the octopus tentacles that I told, which I've shown before. So this is like they have used for the different kind of underwater activation, and it's like biomimicking. It's very important that it can flow. It can actually move like an actual octopus arm. Right? Flexible gripper, different kind of gripper we have. You can see like it's basically pneumatically actuated. You can see different object can go. So the limitations and the advantage you can see is like it has no such certain limitation that it can damage any object. So it has a complete flexibility, and you can see this human hand kind of mechanism. You can see in the grasping mechanism. It's so so good in biomimicry actually. It can be achieved mostly by the pneumatical actuation. Okay. So if you are looking for flexible grippers, because always soft robotics gripper can't take much payload actually, because there is going to be leakage of air and all. So you can go for the flexible gripper as well. There you can go for like the how you're making the manipulator. You can also go for the tendon-driven gripper as well. Like this is like a mini manipulator, but it won't be called like a soft exactly. Many people call it, but I call it like a compliant gripper or flexible. Yeah. So gripper control, I think I'm not going deeper into that, but yeah, so you can actually use the PID controller and all and try to control whether if it is tendon driven, then the more resolution. So that's all from my side. I think I'm open for questions if you have a question. Thank you.
Yeah, anyone from the participants have any questions, so they can directly ask to sir.
Thank you, sir. I had one question. You mentioned soft robotics and for space exploration. The one huge limitation of that is like we don't know the terrain, and there's always like extreme conditions in space. How do we deal with that with soft robotics?
So see, first of all, there is something called space hazards. It's starting with radiation. Then you have like the huge vacuum when it's orbit not nearby to any like natural satellites or planets. So first of all, the soft robots, it's not only the soft robot, it can be like the hybrid soft robots, which is like the let's say for example, it looks like a biorobotics, like a biomimicry of any creature. And you have to assume that let's say there is a possibility of landslides, more like suddenly the earthquake, obviously it is Mars quake or moon quake, whatever. So you have to understand that that kind of possibilities are there, but the advantages here, like if you see about any wheel robots and all that we already send, like the robots and all, it can't go to certain like some slopes, and it can't actually walk up on that, but soft robot actually can do. Number one. Number two is like you can also make different kind of material science, like you can use different kind of advanced material science for the skins and all, which is actually like self-healing. like the one of my like colleague, like scientists from Pond University, they're working on self-healing sort of fingers and all. So hydrogel and many other things. So that kind of things you can actually use. These are already nothing like new, already patented or already people have published papers. But the point I want to make, like, it's not single thing that you are going to use. It will be combination of different things based on the specific reason. For example, if you're going for the dark region of moon, you are not going to get any light. So maybe you have to think that, okay, my timeline is hardly, let's say, 1 month, for example. In a month, actually, you have to complete everything. So your soft robot can have that kind of module. There might be a combination of rigid and soft robot. So rigid body is like I said, the soft robot, and soft robot is going to do something, or that kind of plan. So you can actually make a master slave soft robots based on that. Master slave set of robots where one can be soft robot, one can be rigid, whatever. So this kind of concepts are already there, but depends on the requirement and specific application you can do. So for example, there is a conceptual module called, I forgot the name of the module, but it's basically for Europa, the I think the one of the natural satellite for the Jupiter. Okay, and it's like the ocean of different gases basically. So they're actually trying to make, like, it's basically a plan of a European Space Agency. They want to make a squid kind of soft robot to explore that gaseous, like liquid gas based oceans for this Europa basically. So as I mentioned, like specific application, specific structure that you can do. I hope that I just gave you also.
Thank you, sir. That answered my question.
Sir, you discussed about origami robots. Is it possible that in future we use the technology of origami robots for teleconsultation and remote analysis and diagnosis?
Yeah, why not? So, see, imagine that I'm just giving one case study. Imagine that there are a lot of in surgeries. Channel means I'm trying to make, like, it could be the throat, it could be nose, it could be ear, or anything where the channel size for the human body is very small. You can't make you can't make some device which has like bigger die or huge, like area or something, or like volume, and it can't go inside. So you need something which can enter like smaller version, and then it will basically become bigger to capture something. And that is one of the nature papers actually. If you, I shown one of the crawling robot. One of the nature papers you can see, they're actually making magnetic field control based some material actually that is actually like actuating, like moving as per the magnetic control. And this is quite like prominent magnetic control. It's nothing like the performance rate is like increasing nowadays. So they're actually making very tiny robot which can crawl. Imagine like you are making arch kind of piece of paper, look like arch kind of things, and it can actually walk. So imagine like that. Okay, and then it's going, and then it's actually holding some sort of object or stone inside certain body parts, and then or blockage, and then coming out. So it is obviously possible, but you have to see how you're using. Again, medical application and space application, very important that where you are applying, how you are applying actually. So you have to check that thing very clearly. So that's the thing. So you can't make everything universal. One of the manipulators can be good for the lower body surgical possibilities of thing, but it's not the same thing for ear or nose. So you have to be specific to the specific reason, specific application, and the structure that you are actually going into with the robotic. So I hope that is what.
Thank you, sir.
Sir, I had a question regarding the soft robotics which you conveyed in the slides. Generally, soft robotics, the robot can be operated in two modes. One is the autonomous mode, and the one is controlling the robot using an external controller. So, sir, when we use an external controller to control a robot, generally there is a lot of latency involved in transferring the data from the controller to the robot, and this is called like teleoperation. So, sir, how can we solve the challenges in the latency in the teleoperation?
So I think before you're going to the control thing, first to see, I want to give an example, but I think as we're actually working on it, I can't give the detail, but I can give you one example. Uh, so let's say I'm working on a surgical robot, which is basically a lower body surgical robot for certain specific application. And there, first you have to understand that how your application demands the structure. I mean, the surgery, or let's say certain kind of assistive tools, whatever it is, whatever your application is, how your basically the robot is demanding, how your particular surgical environment is demanding the particular requirements. That is very important. The number one. Then you see whether that extra things, that whatever control and all the stuff that you're talking about, whether it is really going to help you. Because when I told about the human robot collaboration or interaction, HRISRC, there I told there is something called master slave robots and the Da Vinci and all. So basically, decision is taken by the doctor and the robot is making the precision, basically, the medical industry as well. So there, no, it's like a semi-autonomous tools. You can't call it like a robot because, as you told, latency, even a lot of errors. It can be if you go for flexible robots, soft robot, there are a lot of structural damages that could be repetition is not possible in soft robots most of the times. So this is the problem, a fundamental problem. You can't eliminate. So you have to see that whether you need to do those things, or you can actually fix that robot semi-autonomous tool in certain level where you were actually solving the problem, but yeah, you need some human help. That is the stage we're at the moment. But obviously, I think if we can make the robot super intelligent and we understand that, okay, the basic problem can be solved by other material science or maybe other mechanisms. So alternatively, it can actually give a backup support. Then I think there's a possibility, but still, that's a big question. You have to limit your requirement, limit your application based on the particular sensibility. So I hope that's the answer.
So thank you, sir, for taking this session and answering my doubt.
Thank you.
You mentioned something about robotic skins. I was reading about it a few days back, and it was really interesting how the same skin can perform different functions like gripping or mobility. How can the same skin perform these different functions, and also where can we see its application in the future besides in aerospace?
So robotic skins, already you can see that there is something called xenobots. Those are made of not only skin, it's like original frog stem cells. Xenobots, exo-bots. So it's called xenobots. It's by Purdue and some other university. They have collaborated and developed it. In Corona time, that is my favorite robotics games actually. Anyway, so basically, you can actually make stem cells based robots. Those are coming from the chemical engineers nowadays. Also recently, scientists developed robots made of some paste composite, which is semi-liquid or semi-solid, something like that, and it can actually work again. The this magnetic field control. That's a wonderful thing. Actually, it's not just some unidirectional. That's the beauty. Anyway, so when you're talking about robotic skin, so it has certain things called flexible electronics and flexible skin, where mostly it's sensorized and all, and there is some concept called haptic feedbacks and all. So these are the part of things when you come to assistive or medical robotics. So they are basically to understand that what is happening. Till now we are understanding that we are characterizing the tool. Let's say I'm using some robotic tool, I'm trying to understand that, okay, what is the limitation of a robotic tool, what this robotic tool can do, can't do, what are the maximum repeatability case, and if whatever additional things I'm using, let's say robotic skin or sensorized skin, whether it is okay to use in the surgical environment or not. Okay, you put inside water, it is not good, let's say, but there is some certain organic things inside body which is reacting to human body as well, and it's also it's dynamic like that. So you have to understand how to use, where to use, and then you have to, based on that, you have to take the decision that, okay. So mostly I think the medical science is the best place, surgical environment. Some cases you see the wearables nowadays coming, right? So in the wearables, actually you can actually see that wearable skins or maybe that AMOLED display and all these kind of things, which is flexible displays are coming actually. So apart from that, I mean, I don't call it a robotic, but obviously flexible electronics, you can call it like a kind of external version or part of a robotics or something, this same community. But anyway, if you are using with some robotic application, obviously it's like a wonderful thing. And mostly you can use it in the screen-based display, or nowadays people are talking about like different kind of space shoots. Already NASA is developing space shoots and all. Elon Musk is like, I think if I'm not, they're also collaborative developing new kind of space shoot, like, and the different launch you can see the NASA solar space shoots are different. And so you can make like different kind of textiles where you can actually use this. So there are a lot of applications. These are already happening in the world. It's nothing new. And also you can make like sensorized human dresses. That is one of my plans in future actually. So where you can actually make sensorized human dresses where you can get a lot of data from the dress itself. It will be intelligent dress actually. So if you want to wear that, you can access things also. I hope that is the answer.
Thank you, sir.
Sir,
Yeah.
sir, in one of the slides you showed some bio-inspired robot. The white color one, it had 6 legs. Sir, can you tell how did you make that robot? Because I've seen such kind of robot, but they normally use a lot of sensors and a lot of different parts. They use a lot of microcontrollers and all, but I couldn't see any of them in the model that you showed. So can you
Yeah,
give a
these are obviously my own work anyway. So, see, this is very important. First of all, you make 3D printed module, whatever size, then that's the mold. You put the silicon, silicon will become the shape according to your requirement, desired shape it will come. And then you see what way you actuate, whether you will SMA or you can go for pneumatic, based on your application again. Pneumatic has certain limitations. SMA based, you have the limitation. I'm taking these two actuation methods because you can actually go for the miniaturized version. For other cases, it's like difficult to go for miniaturized version. You can go very small size and still it can actually move actually. So I think this is the thing. It is fundamental for any software most of the time with the silicon based. Apart from that, there are also like PTMS and all, and then different kind of organic materializing. Those are like again chemistry people can do. I'm not into that area, but nowadays people are doing. So everybody is doing robotics actually with chemistry, with organic chemistry or PTMS. The PTMS with like with the power it can actually give some actuation. And nowadays the tiny, very tiny paper like grippers are coming, which is made of again the PTMS and all. So like it's like they're playing with the material science basically, and then they're changing the voltage or maybe current or maybe the temperature or maybe based on their sensitivity, and they're just playing with that, and then they're getting something. It's like very interesting actually. So yeah, this kind of things, and it can also, you can call it like an intelligent skin, which is giving us sensitive skins and all. Okay, and then you are applying. So it's a very good way to explore that. So I hope that I answered you.
Oh, okay, sir. Got it. Sir.
So I have a doubt. Because the medical and the health industry is switching to machinery for the future surgeries and all, is it possible that the technology is making the doctors less skillful as they will be more dependent on machinery for surgeries in future?
Yeah, so this is a very fundamental question. I think when the robot has been introduced for the medical industry, that is the fundamental question. That's the reason the human robot collaboration is coming. Master slave robot is coming. I mean, I'm talking about the terminology, not robots. The terminology is coming. That means decision by doctor, performance by robot. Now, for example, I want to mention a movie, sci-fi movie, Prometheus. Those kind of space missions where you might need some like multitasking surgical robots. I'm talking about maybe like, I don't know, 100 years after futuristic robots where the robot can take decision and do anything. Or maybe that if you see the Spider-Man Far Away From Home, I'm talking again, giving sci-fi example. They're making the Spider-Man shoot inside some tubes and all. So this is like, actually it's possible in certain extent at the moment, not the perfect one that you see, but so this is basically like, if it is not affecting, that's what I'm saying. It's about the human intelligence, sorry, robot intelligence. That means if the robot, for example, robot needs to, you program it that you first to go here, then you see the COVID patient, and COVID patient A, COVID patient B, COVID patient C. For COVID patient A, you increase the oxygen level. For COVID patient B, you give some vitamins or food or something, and COVID patient C, you just decrease the oxygen level because he or she is better than earlier. This is simple. It can be done. Okay. Now you have a complex scenario where you have life risk. That moment, if you don't have the robot that much inclined to take decision, obviously you just take it like a precision. For example, stitching. There is a Da Vinci robot surgical kind of example is given. So they are taking grape and they are peeling the skin of the grape. It's so good. I mean, it's like so precision. It's like it's like the example of precision and intelligence actually, because the pressure, how much to get, how much, how you have to inject that syringe or the basically the needle and all, and then it will be stitching also. So that pressure is also because it's a very tiny grape, a grape actually. So you can understand also precision. So that you'll love it like when you see that kind of. So basically that's the thing. I think once the robot is enough intelligent and enough experienced to handle this kind of stuff, obviously why not? But till that, no. Till that, doctor will be there always taking decision, and robot is always there for taking the decision. Yeah, that's the partnership model. Have this that.
So,
Sir, I have a small doubt.
Yeah.
So I have a small doubt that when is a good time for an individual to shift from manual testing to an automated testing?
Can you be more specific, like what testing you're talking about? Like
Sir, there are many tasks that should be done automated testing that does not require a manual work. So, but there are some tasks which require manual work. So how
can
can
you
we
give one
distinguish between
example?
them?
I'm asking, can you give an example? I think that would be more specific then. Just give an
Sir,
example.
there are the tasks which requires multiple things, multiple repeated things, require automated testing. But for an individual, for a normal task that can be done by individual, that does not require an automated testing. So I'm just asking, when is the good time that an individual shift from manual testing to an automated testing?
So I think if you think about the principle wise, then I would say that when you need more accuracy with respect to time, the better performance, better accuracy, more number of tasks to be done, and that is possible by the autonomous setup, then why not? You should adapt the autonomous setup for that. But if the autonomous setup is not able to adapt certain things according to situation, for example, in a certain time standpoint, like maybe let's say you started with let's say x time and then you have x plus 1, x plus 2, x plus 3 time. Okay, in particular every hour or every second the task that you're doing, the nature of task is changing and the robot is not able to the autonomous system or robot is not able to actually detect that or actually judge that because it doesn't have that intelligence, right? So obviously will not go for that, which is same repetitive task. Why not? You can go for robot will perform the best. If you have like the task which has certain difference from the previous stage to the next stage, then obviously you need like decision making things. Would be with the robot, obviously you can have some sort of intelligent robot. Nowadays, Rubik's cubes are solved by robots. Okay, how many turns this side, that side. So it's intelligent robot, obviously, right? With the color and camera and everything, it's possible. But it's only the Rubik's cube. You give something else, it can't move also. So like that. So you have to see that specific task and repeatability and speed, and these are the factors. If it is okay, right, you can go for that kind of automated version.
Okay, sir. Thank you for the explanation.
So this is Joel here. First of all, it was an amazing session, sir, and thank you for it. Then I have a question, sir.
Yeah,
Yeah,
can
today-
you be a little louder?
Yes, yes, it was an amazing session, first of all, sir, and thank you for it. And the other day I was reading about flexible robots used in cancer treatments, sir, most especially in nasopharyngeal cancer treatment, which basically occurs in nasopharynx. And even I came across that such robots have diamond perforations. If you can provide a short overview of such robots used in such type of treatments, it will be helpful, sir. Basically, yes.
Thank you. So this is very specific surgical tool based question. So if you see, there's a trend of hollow tube based or tube based surgical like robotic surgery or something like that. It's called robotic assisted minimal invasive surgery. RAMIS or RMIS, whatever it is. Even you can find like flexible robotics based minimal invasive surgery, something else that you can find. Anyway, so that are like the more niche field. So anything that you have a in body part, like inside human body, you can see that there are a lot of curvatures, there are a lot of like, I won't say as an angle because those are like soft muscles, soft tissues. Okay. So it's like flexible or you can say soft and like the tensile strength and all these mechanical properties are like very soft actually and very sensitive also. So it's like kind of an intelligent, if I use like the robotic term, it's like intelligent skill. If I use the word. So in that case, you need continuum kind of robotic arm, whether it is small size or big size, whatever it is. Obviously, not big size because you're not dealing with big creation, you're dealing with humans. So you need whatever the particular role of application the surgical whatever to go for that. So if it is nasal, so you have to obviously design which can actually go with the nasal and the distance that you want to cover. For example, you are going for the lower, how much you can actually maybe assume like the maybe which is like the external part of that particular gap or hole that much. So then you can go with that kind of diameter, inner diameter. But if you're going for again inside, okay, and then like how they're nowadays that COVID test, they're putting that swab actually. Then you see the swab size, right? It should be even smaller than that because there is a curvature and all. Okay, that's the reason you mentioned about time and shape. So basically, you have a requirement of each and every module can actually rotate. Rotate means like bit of like let's say like how can I say like theoretically like I want to talk like let's say it's basically like a component way, but I'm just trying to make like it can actually it has a flexibility as a whole, but it is also have a flexibility for flexible move as a single unit actually. Okay, sidewise or ups and downs you can't, but at least sidewise you can see that. So that's the reason you can see any design. They actually make like on the top one is like the planar, the bottom one can be like little curved or there is this little cut in the surface. So it's basically give a space for the next one to move a little bit. So this way it can actually move. And that's giving the little bit of like, flexibility. It's increasing the flexibility basically for the robot actually to move from each and every part and then the curvature. So one of the tube-based robot I'm actually developing that I'm really like maybe next year I can talk about. So there also the flexibility and all, and then I'm trying to make it as simple as it's possible, easy to control. I'm trying to increase the repeatability until it reaches the it kind of a rigidity. Though it's flexible, but still can reach the rigidity based on the structure of material property. So those kind of stuffs are there. So based on that, your application you have to go. So I'm mostly working on the lower body surgical robotic system, but the thing that you mentioned is like laser or that kind of cancer, that treatment. So you have to make that kind of gripper, small gripper, which is able to take certain payload or certain payload means it's very tiny, but obviously it's very sensitive because it can't damage anything. It's very important. Surgical, whatever the object or the surgical particular position, this is already damaged. You can't damage. You have to basically repair it. So you can't put it something which can actually damage. So you have to be very careful about the material science, the structure that is you are designing, the curvature it can move with your tendon driven system. Mostly tendon driven is best, or magnetic or whatever. So based on that, I think you mentioned. So that's the kind of answer that I can give.
Got it, sir. Thank you. Thanks a lot.
Anyone has any more questions?
Yeah, you can ask anything. I mean, if you have any other question apart from this session, also you think that I can answer this.
Yeah, I think sir, everyone has asked their questions. It was a very nice session, sir, and interesting and informative too, sir. We got to learn a lot of new things, and it has surely opened our minds to a lot of new avenues. And I'm pretty sure every one of us has to take a lot from you. Thank you so much, sir. Thank you so much for your time. Thank you so much, sir.
Thank you guys, and yeah, happy to come back, and I hope all of you are like safe and stay safe also. COVID is coming, so stay safe and keep exploring and keep learning. That's a great thing to do something
Thank you so
interesting.
much.
Yes,
Yeah, thank you.
Thank you so much for the great session, sir.
if any doubt, they can contact you on your LinkedIn as well. Yes.
Yeah, sure. They can contact on my LinkedIn. Also, just I want to take this opportunity. Like we do a lot of papers now. I have as I already see that we have something called Space Mess International. I'm the chapter chair, so I'm like my motivation to do this thing is like to make different kind of papers basically, like where we are taking a lot of people to as an intern, online internship, and then they're actually like working with us or as a team member, can different kind of roles are there, and they can actually we try to publish in papers actually mostly online if funding is available in non-profit chapter, so no fund very frankly, but we try to do most simulations. But if somebody is interested to make like 3D printed and all this stuff, they're doing. So, we got like people from NIT, IIT. I got someone from VIT as well. Except Rahul, I think there were more girl called Kanishta. She's in Delft now. I think just so one of your alumni. Yeah, so like that. So if people are interested, that kind of stuff, it might take little time, like 2 months or something, because online you understand part time online 2 to 3 months. But if everybody is interested, we can actually do a great thing sitting in home. I believe that theory. And it's successful. So a lot of people are doing that. So presently I have some NIT guys as well. So yeah, something if you're interested, I'm very happy. I also do a lot of support to the students, different level for the university department and all. So anything if you think that is possible by me, I will be happy. This is the second time I think I'm coming, so I'll be very happy to work with you guys further. So thank you for inviting me again. Yeah, happy to support guys.
Thank you so much, sir, for the session. And uh, just tell us more. How can these people approach you for internship that you were talking about?
Best if you guys are like coming like like say many people, then email is the best with the list. If you are like coming like 1, 2, 3 people, like obviously take the reference and just better you can just WhatsApp me. I don't have any problem. Just mention that you've attended my session and you're interested in this kind of online internship from the non-profit chapter. Forget about the internship, even just publishing a paper itself is possible. It doesn't matter. And then we can work. It's very simple. Like you can share my number, but make sure that don't send so much messages because I am having a lot of calls from my startup and international things that it is very normal thing. So just message me once, and then according to, and also you can message about like your interest, like something that I want to do in this, and then I want to see that if it is feasible. Obviously, we can do. And if you are like coming as a group, one person can communicate, and you can actually make a balanced group, like one person from mechanical, one person from EC, something like that. A little bit of robotics knowledge, this knowledge, that knowledge, and then according to your strength, we can actually go from the papers also. So mostly target journals. So simple free journals are not whatever impact factor, Google Scholar or Web of Science, whatever standard thing. So and we work for 2, 3 months, and then we go for it. So something like that also. And it's unpaid because non-profit chapters, something else. So if you're comfortable with all these certain conditions, then please feel free to message me. I'm comfortable to chat on WhatsApp more than and any email. It's okay. Anything.
Definitely, sir. Thank you so much, sir, for giving this opportunity.
Thanks. Thank you.